Thank you, Mr. Martins, and thanks to the organizers for including our paper in the program. I'm talking about early crack growth from notches under creep fatigue loading, and what we see here on the left is a turbine shaft. And due to the design of these components, we have a lot of notches, like you can see here in detail, a blade groove. And the load, or what you usually do in your lifetime assessment, is to look for where the load is concentrated, and this is of course here at the notch root. And what is then done in your lifetime assessment, you determine your local loading and go into a fatigue life curve, like you can see here on the right, this black curve, and determine your number of cycles to crack initiation. But what is completely neglected here is the effect of notch support, which comes from the stress gradient, which you obviously have here. And if you consider this in your determination of the number of for crack initiation, you end up with this red curve. So this lifetime beneficial effect, in my opinion, needs to be considered here. And our basic principle to do so is at first an experimental determination or quantification of this effect. So what I already said is we would like to determine the number of cycles to crack initiation, and here we need to define constant crack depths to deal with, and this is in our case 1 millimeter. And we investigated the number of cycles up to 1 millimeter with different kinds of specimen geometries. The standard is to use a uniaxial standard LCF specimen, and we use then a round bar specimen with a circumferential notch to determine this effect. And you can see by these schematic bars here that the cycle number is much higher for the specimen with the notch. And we do the tests in our high temperature lab in Darmstadt here. You can see one of our test rigs where we load these specimens with a cyclic mechanical loading and a high temperature. In this case, I'm talking about heat-resistant steels, so we have temperatures of 600 degrees Celsius here. The temperature is controlled by thermocouples. You can see here in the LCF regime, we typically do strain control tests, so we need an extensometer to control the displacement. And we measure this crack growth by using an alternating current potential drop technique. So the one important thing I already mentioned is that we are looking for same crack depths, and the second important thing is that we do this comparison of cycle numbers at the same local loading level. This is really important here. Yes, we not just did these tests with one notch geometry, we did it with different notch geometries under different loading conditions. We have a pure fatigue cycle, this triangular shaped cycle here, and we have a cycle, a trapezoidal cycle, with an additional dwell time of 3 minutes in tension and compression to investigate the impact of creep. And the results are already given here by fatigue life curves. You have the local loading level here on the y-axis and the number of cycles on the x-axis. For a 9% glowing cast steel at 600 degrees Celsius, just as an example here. We investigate a lot of other materials as well. The standard fatigue life curve is this black one here, and the markers, the red markers, belong to the standard tests, and the blue markers belong to the mild notch, and the green ones to the sharper notch. And you see already that the cycle number for crack initiation or for a crack depth of 1 millimeter is much higher in the notched specimens. What you see furthermore is a blue and a green line. And this line comes from our computational approach to determine this cycle number. And I will talk about this using this slide here. Our computational approach is based on a cyclic elastic viscoplastic simulation. So we modeled this part here of the round bar specimen with notch. And we apply a bilinear material model for the elastic plastic part and the modified Garnatt-Fowler-Creep equation to consider the creep behavior. And then we use one mesh from the beginning until the end of our simulation to keep all the information about plasticity and viscoplasticity. And we release nodes to let the crack grow. You can see here the plastic wave. And this is important to do so to consider crack closure effects raised by plasticity or viscoplasticity. To determine now the crack tip loading, we use a cyclic J integral, and this is determined by the global force displacement curve, which you can see here in the middle. And to get a cyclic value of the J integral, we reference the global forces and displacements to the lower point of load reversal for determining the cyclic J integral for the upper loading branch. And we reference the values to the upper point of load reversal to get a value for the lower hysteresis branch. Yeah, here on the right, it's just the basic fraction mechanical concept to make a comparison or to compute the energy difference for two crack configurations, A and A plus delta A. And yeah, we end up with the cyclic J integral, already considering crack closure effects. So these are just formulas I think you're all aware of. For the fatigue crack growth part, we use Paris law, but here maybe the difference is that we use the crack tip loading delta J effective for the loading part and for the unloading part, so we differentiate here. And we use a Nickman-Swift-Matster model based on a CT average parameter introduced by Saxena to determine the creep, to compute the creep crack growth rate. And the sum of both fatigue and creep gives us our creep fatigue crack growth rate. And the model, the parameters of these models are determined by independent standardized tests. Now I would like to focus on one major finding we made here during our investigations, and this was the impact of the dwell times on crack closure. What you see here is the delta J effective value over crack depth for the case without dwell times. So you see that these full and blank symbols here, they belong to the loading and unloading part, and they are almost equal during the cycle. On the right you see a measured hysteresis curve, force displacement curve, where you see kinks indicating crack opening and crack closure. So for fatigue loading, everything is fine. We end up with the same results for loading and unloading. But what happens now if we add the dwell times of 3 minutes in tension and compression, we end up with a huge difference in crack tip loading. You see here for the loading part of the hysteresis, we get much higher delta J effective values. And this is already shown here in our experimental measurements. You see a kink in the unloading branch indicating crack closure, but you can't see a kink in the upper branch indicating crack opening. So this tells us the crack is already open here during this dwell time in compression due to relaxation. And this is a very important finding, which enabled us to pretty good describe the crack growth. You see the crack depth over the cycle number. These blue line and these blue markers belong to a pure fatigue cycle, so this is no big thing. But the black line here and the black stars, they belong to a creep fatigue loading. And this is just possible because we consider the effect of the dwell times on crack closure. And if we do so, we end up with a higher fatigue crack growth rate during our creep fatigue loading. You see the difference here. And of course, there is an additional creep crack growth occurring. So in the end, the sum gives us here a very good description of crack growth on the creep fatigue loading. This is just one example. I would like to show you here on this slide that we did some more tests, different loading levels, different geometries. You can see here by this plot where we plotted the computed over the measured notch support factor. Okay, short introduction of the notch support factor. It's just the ratio of cycle numbers for a notched and unnotched specimen. This is in the end what is interesting for the industry to have. And by this plot we see that we are able to compute the crack growth, the early crack growth under green fatigue loading. We get notch support factors for the mild notch of around about 2. For the sharp notch we get factors up to 9. And we did some more tests and computations on other specimen geometries. You can see here a cruciform specimen with a central borehole acting as a notch. We applied uniaxial and biaxial loading here, and as well for these cases our computational approach worked very well, and we compared the results with experimental results and end up with a notch support factor of around about 4. And this scatter band is plus minus 2, so this is a very good result. Let me conclude. I showed you how we compute early crack growth from notches under green fatigue loading. I showed that we use different geometries, different loading conditions, and different materials. And I pointed out one major finding here, which is the impact of dwell times on crack closure. Of course, there are other time-dependent effects which act on crack closure. This was what we observed for low-alloyed steel. Their oxidation-induced crack closure is as well very important. Couldn't talk about this today, but we've seen this. And in the end, using the notch support factors, you can definitely improve your lifetime assessment of your component. Thank you very much.
Thank you very much for your presentation. The paper is now open for discussion, questions or comments, please. Okay, I have one.
If there are no questions, I might. Thank you very much for your presentation. I find it very, very interesting. I missed probably the part where you say how do you implement it numerically? So you have your differential equations. How do you get the number of cycles to?
By integrating the crack growth laws.
Okay.
Comparison.
So scalar equations, let's say, for 1 point, for 1 temperature, you get one.
Yeah.
Okay.
Yeah.
Okay.
Very, very easy use case here.
Yeah, absolutely. But thank you.
Any more questions or comments? I have one question, please. About your dwell time. What was the duration of the dwell?
3 minutes.
3 minutes. Do you think you have grip in 3 minutes? Or
Yes, of course.
Of course. And the oxidation plays an important role also?
As well, yeah.
And about the finite element modeling that you have done, you calculate the local stresses in the notches, or that was the purpose, to calculate the local stresses? When you present the viscoelastic analysis that you have done, you were determining the stresses in the notches, yes? Or not?
Yeah, of course there are stresses around the notches, but
do you use the calculations of the stresses in the notches for your predictions? You can
yes, not explicitly, but
yes.
So we were more focused on the global force displacement curves to determine this energy difference.
Yes.
And I looked in detail on the stresses along the crack path during the dwell times, what happened with the stresses. I didn't show it today here, but there we clearly see a relaxation during the dwell times because we're in strain controlled conditions. So if we have this dwell time in compression, the stresses along the ligament relaxes, and as well the stresses along the crack flank relaxes. So if we then apply again a load, you don't need much load, and the crack is already open. So that's why the crack tip loading increased.
Thank you very much. Okay.
Thank you.
So the next paper that will be presented, I do not know if the